Once you have tasted flight, you will forever walk the earth with your eyes turned skyward, for there you have been, and there you will always long to return. Leonardo da Vinci. Wait, hold on, this isn't the right place. Let me just... Nope, not here either. Keep going. What in the... Much better. Now, to say that I like paper airplanes is a bit of an understatement. I was obsessed with these things as a kid. And to be fair, I owe a lot to paper airplanes. I mean, they arguably got me into a lot of the topics that I talked about in this channel, like physics and math and differential equations. In fact, the first video on this channel, which is about fluid dynamics, the Navier-Stokes equations, and by extension, turbulence, is a direct result of me studying paper airplanes. So making a video like this was, in my opinion, naturally the next step. See, believe it or not, this actually isn't the only kind of paper airplane. There are actually hundreds of other designs, and a lot of them do really cool things. Paper airplanes were the things that originally taught me math and physics, so I think it's only right that I use math and physics to create a really, really cool paper airplane design. And I'm not just going to make any old paper airplane design. No. I am going to make the fastest paper airplane in the world. And not just because Guinness doesn't technically claim this as a record that they can mark. So if I just theoretically make a video that records this and claim that it's the world record, then it is the world record. Because at this point in my life, I think I have enough math, physics, and paper airplane expertise to actually make this a reality. But wait, before we begin, we gotta set up some rules. Rule number 1. This paper airplane has to be flown on real-world Earth conditions, on the ground, or close to the ground. The reason I'm saying this is because scientists actually have tried to create really fast paper airplanes before. The problem is that in order to do this, they basically cheat and fly their planes under unrealistic conditions to artificially increase their speed. Not only, in my opinion, is this disingenuous to the entire point of a paper airplane, in that it's essentially a marvel of engineering that simply allows a paper to fly by the way it's folded and nothing more. Also because of the simple fact that I think most people, including myself, don't have the capability to fly paper airplanes in near perfect vacuum-like conditions. Anyway, moving on to rule number 2. Folds only. No tearing, no cutting, no gluing, just folding. I'm sorry NASA, but if your fastest paper airplane requires tape to be made, then it's not a paper airplane, it's an art project. Pencils, pens, markers, and other writing utensils can be used to plan out the design, but nothing more. Next, rule number 3. It's a paper airplane challenge, so it actually has to look like an airplane. The way I'm defining this is that it has to have a very clearly defined head and wings. So, although this tube thing definitely looks cool, it's not a plane, so it definitely doesn't count. Also, I'm pretty sure to make that thing specifically, you'd have to violate rule number 3, so yeah. Finally, we have rule number 4. Only one sheet of paper can be used. I think that one is pretty self-explanatory. Anything that falls within these 4 rules is completely fair game. Anyway, rules out of the way, let's get to the fun part and do some basic testing with the classic dart shape. Yeah, low-key, I thought basic testing would be a little bit more exciting too. But it's fine. Let's rewind the clip a bit to see what exactly makes the plane move like that. There are 4 main forces that give the plane the movement that it has. These forces are being represented by vector arrows. What's nice is that we can actually just ignore 2 of these forces. These vectors actually fall into 2 different groups. One which controls whether the plane can move forward or backwards, called the x vectors, and one which controls whether the plane moves up or down, called the y vectors. These movement vectors are actually independent of each other. What a plane, or frankly any projectile, does in the y direction will not affect its movement in the x direction. So we can just comfortably focus on the x arrows. And these forces actually have special names. The one that's moving the plane forward is called thrust. And frankly, we really don't have to worry about that one that much either. Thrust is almost entirely determined by the strength at which you originally throw the plane in the first place. It remains constant throughout the flight trajectory, so we really don't have to worry about it. When solving for our shape, we might include a plus t term to represent the constant force of thrust, but it won't actually affect the shape itself. Which leads us to the final force, and the one that we actually do have to care about. Drag. Drag is the natural force of resistance that occurs when fluid particles hit a solid. Or in other terms, it's basically friction in the air. Creating a paper airplane design that minimizes drag is the same as creating a paper airplane design that minimizes the only possible resistive force to paper airplane movement. Not only creating the most aerodynamic paper airplane, but also the fastest. And luckily for us, there's a formula for drag that we can use. So let's use it. Shown in this animation, one way to define a function's minimum and maximum values is to essentially set its derivative or rate of change equal to 0. This seems random to bring up right now, but it'll be important later on. What you're seeing right now is the formula for the force of drag. We're also making the assumption that the force of drag is equal to the net force. The main reason I'm doing this is because, as discussed earlier, over time, thrust is a constant. As a result, it shouldn't actually affect the shape of the plane. Also, this is an engineering video, not a math video, and rigor is dumb, so. Anyway, 3 of these terms are constants, so we can merge them and treat them as such. This leaves us with u, the velocity term, and a, the area term. Based on the definitions of velocity and area, we can rewrite velocity as dx over dt, and we can rewrite area as the integral of f of x with respect to dx. Okay, now this is where the cool part comes in. Because f of x is a function that directly contributes to drag, we can treat drag as a function of f of x. This function of a function has a special name. It's called a functional. And in a similar way to how we can take the first derivative of functions and set them equal to 0 to find minimum x values and points, we can take the first derivative of this functional and set it equal to 0 to get a differential equation that, when solved, will give us functions of x that minimize drag. This technique isn't new, by the way. It's called calculus of variations, and it's been used historically to find a lot of shapes of interest. Anyway, when you solve it, you'll get this equation, which when plotted on Desmos looks like this. Given the shapes of planes, bullets, and other things that are designed to be aerodynamic, I think this equation is pretty accurate. Now the next step is to actually design the paper airplane in a way that it looks like the graph. Making a curved paper airplane from folds alone may seem impossible. However, it's very possible if we're able to understand how paper airplanes are folded, and by extension, how they get their shape. And to truly understand that, we're going to take this normal paper airplane, unfold it, and then refold it again to really see what's going on in each step of making it. When unfolding it and refolding it, there are 5 clear visible steps to making the classical paper airplane. Step 1 is to fold the paper in half. Step 2 is to fold the corners in to make triangles. Step 3 is to fold over the edges to shape the plane. Step 4 is to fold it in half again, and step 5 is to fold out the wings. Step 3 is the important step here for us because the linear fold in that step shapes the plane to be triangular. So if we're going to make a curved paper airplane, the main thing we have to change is how we fold our plane in step 3. What I did specifically was that I traced the curve onto the paper directly after I finished step 2, and then I proceeded to carefully fold along this curve during step 3. This took a little getting used to, but I got the gist of it. When it was done, I just followed steps 4 and 5 to the best of my ability, and voila! We have ourselves the world's fastest paper airplane. You can see how the paper airplane is different than its classical dart form in the sense that it's a little bit more rounded towards the end and resembles more of a paraboloid than it does a triangle. In my opinion, this might be also the coolest paper airplane I've ever made. I mean, it looks like something out of Star Wars. Now, it's one thing if the paper airplane looks nice, it's another thing if the paper airplane can actually fly. To do that, we have to actually throw the thing and test it out. And I think there's no better place to test it out than That's right, one of the top research institutions in the country, and the place home to our best students, biologists, chemists, mathematicians, physicists, engineers.
And me. That's right, I'm at MIT, and I'm gonna test these planes here. I feel like it would be appropriate because this is kind of where like all the funny engineering stuff happens, and realistically, I've seen the admission rates. This is probably the only time I'm going to be here, so I may as well make the most of it and then get my views while I can.
Yeah, I think it worked pretty well. For reference, by the way, all of those clips were upwind, so I wanted to see how the plane would fare in the worst possible scenario. I think it fared pretty well. But perhaps the most notable thing about the paper airplane is that it spins when it flies. Just like a bullet, the natural spin of the plane allows it to be faster and more accurate, giving it a significant advantage over its classical counterpart. But for those of you who are still doubting, I tested this plane under the original conditions which I tested the classical plane before, aka off my stairs. For reference, both of these clips including the setup, took 2 seconds. The plane could have probably traveled even further had it not been for the wall window thing. If anything, I think the plane worked a little too well. And now to name the airplane. And if I'm being frank, I think there's only one name fitting of it.
Is you say daddy's home.